So we were discussing about pseudo force last time. We will continue with that in Newton's laws of motion. Right. So as I was telling you, we discussed about non-inertial frames and pseudo force concept. And we saw that when a body is in a, first of all, we saw a non-inertial frame or a non-inertial frame of reference. This is defined as a reference frame which is in accelerated motion with respect to ground. So with respect to the ground frame, if we are in a reference frame which is moving, but not just moving, but moving with acceleration, that is, the acceleration should not be equal to 0 for the frame with respect to the ground frame, then we can call it a non-inertial frame. And any body in a non-inertial frame experiences a pseudo force due to the combination of two factors, the inertia of the body and the acceleration of the frame. It experiences a pseudo force given by the formula. Okay. This, we understand that it is a force of magnitude ma0, where m is the mass of the body and a0 is the acceleration of the non-inertial frame with respect to ground. Okay. And the direction is opposite. To the frame's acceleration. So this is what we discussed about pseudo force in the last lecture. So let's continue with some example of this pseudo force concept. So next up, we will see this type of situation. Let's consider again an accelerated lift, which is going up with an acceleration, let's say 2 meters per second square. But this time inside the lift, we have an Atwood machine, that pulley system, that kind of thing. So given the mass of the block A is, let us say, 4 kilograms, mass of the block B is 6 kilograms, and acceleration due to gravity is 10 meters per second square, and the pulley is smooth and massless. The thread is also massless, and the elevator moves with uniform vertical acceleration. So now we want to find out the accelerations of blocks A and B in the elevator's frame. So with a reference frame of the elevator, how much is the acceleration of block A and B? Then we also want to find out the accelerations of blocks A and B in the ground frame. Okay. And finally, one more thing you want to find out is the reaction force at the hinge of the pulley. You find the reaction force acting on the pulley through its hinge. So the pulley is like a disc which is hinged at its center. So between the hinge and the pulley there is some kind of reaction contact force. So we have to find that out. Okay. So just try this question out. We'll discuss its solution. So what I suggest you do is to do the first part, you make the free body diagrams of the blocks A and B both individually in the elevator's frame. Make it in the elevator's frame. Okay, so people hope you're following what we mean by the the free body diagram in the non-inertial frame. So what we mean is that if you imagine you have an observer who's standing inside the elevator, okay, then he is in the frame of the elevator. Okay, and that is what kind of frame now? It is a non-inertial frame. So for this observer, it will appear like the heavy block is coming down with respect to the pulley at some acceleration A, and this going up with some acceleration A, but the pulley is at rest as far as this observer is concerned. Okay, this is in the frame. So this A is over here. The acceleration of A or B in the elevator's frame. Okay, and in that frame, the pulley is stationary. In the elevator's frame. So that one we will calculate by making this free body diagram. Okay. So obviously there is some uniform magnitude of tension acting. Okay. So now let's visualize the free body diagram. So in the non-inertial frame associated with the elevator. Okay. Now that frame itself has an upward acceleration of A naught. Okay. We know A naught is equal to 2 meters per second square. So in that, if we look at the free body diagram of the body A, there'll be the forces tension, weight, okay, but there will also be pseudo force, and pseudo force का direction क्या होगा? It will be opposite to the acceleration of the frame. So this will be the pseudo force. This one, and in this frame now we know that this has an upward acceleration of E. So the equation for this will become T minus pseudo force minus weight should be equal to mass into acceleration. So that is the equation for the body A. Now similarly, in the same frame, the body B will be having a downward acceleration E, and same type of forces acting on it. Tension, its own weight, but also pseudo force, which will be its mass into acceleration of the frame and opposite in direction. So for B, my equation will become weight plus pseudo force minus tension is equal to mass into acceleration. Okay. So this we can now convert because mass of A was given to us as much 4 kilograms. Mass of B was 6 kilograms. A naught was 2 meters per second square, and G is of course 10 meters per second square. So this equation will become T minus 4 into 2 plus 10 is equal to 4A, and this equation will become 6 into 2 plus 10 minus T is equal to 6T. Now you can just solve these two equations by adding them. Yes, that's correct, beta. So we will get 6 minus 4 into 12 on this side is equal to 4 plus 6 into A. So that's correct. We will get the acceleration of the two blocks relative to the elevator to be 2.4 meters per second square. So remember, in this, the value of A that we have got, that is the acceleration of the blocks in the reference frame of the elevator. Okay, so remember that here E is with respect to the elevator's frame. So in this frame, the block A will be going up with an acceleration of 2.4 meters per second square, whereas the block B will be coming down with an acceleration of 2.4 meters per second square. Okay, So make sure you note down this and understand this in context of free body diagram, application of pseudo force and Newton's second law. And once you complete this, now we'll come to the second part where we have to find the acceleration of A and B in the ground frame. So for that, we don't have to do anything new as far as Newton's laws is concerned. We have to just use relative motion. I know the acceleration of the frame and I know the acceleration of the body with respect to that frame. So I can use the equation of relative motion to find out the acceleration in the ground frame. Okay, so people, now for the second part, what we have to understand is how we can use relative motion concept. Okay. So as I said, you don't have to get into solving any new equations for Newton's laws. You just have to understand that in the elevator's frame, you are seeing A go up like this, and you are seeing the block B coming down like this. But the elevator itself is going up at A naught. Na? So in the ground frame, what does the acceleration of A look like? So if we have an observer who's on the ground, to this observer, what does the acceleration of A look like? What does the acceleration of B look like? So here we can just use the proper vector notation. Take this as a y-axis, this as a x-axis. So we can see that with respect to ground frame, acceleration of the elevator is A naught j cap. Okay. Whereas with respect to the elevator, acceleration of the block A with respect to the elevator is plus A j cap. Okay, this is also plus. Whereas acceleration of B with respect to the elevator is minus a j cap. Okay. Now we'll just use the simple relation that acceleration of anything with respect to another frame is the acceleration of that thing in the ground frame minus acceleration of this thing. Acceleration of B with respect to the elevator is the acceleration of B in the ground frame minus acceleration of the elevator. So if you invert these equations, it just means that acceleration of A, for example, is the relative acceleration plus the acceleration of the elevator. So this equation and a similar equation for B we'll use. Okay. So now we can see that in the ground frame, so this is plus 2 j cap in meters per second square. This is plus 2.4 j cap. This is minus 2.4 j cap. Okay. So now from this, we will again see that with respect to ground frame, okay, the acceleration of the block A will become the relative acceleration of A with respect to the elevator plus the acceleration of the elevator. So it will become E plus E naught j cap. So the acceleration of the block A will become 4.4 j cap in meters per second square, positive of 4.4. So this is what we are looking for. Okay. So acceleration of A will be upwards. Okay. And now likewise, the acceleration of B in the ground frame will be the acceleration of B with respect to the elevator minus plus acceleration of the elevator. So this will be minus A plus A naught j cap. So acceleration of B with respect to ground will in fact become minus 0.4 j cap in meters per second square. Okay. Or if we want to express it as just a scalar quantity, we can see that it is going to be 0.4 meters per second square but downwards. So in the ground frame, to this guy it will look like the object B is coming down with some acceleration. The object A is going up with some acceleration, but they're different in magnitude. A is going up with 4.4, B is coming down with 0.4. Okay. So this is something critical for you to understand. Please go through this carefully and make sure you understand this notation over here, how we use the relative motion concept. Okay. So first of all, make sure that you understand the notation of relative motion properly here. Just a second. I'll maximize this again. Yeah. So make sure you understand, this set of equations here. Now, this is the theory of relative motion. Harsh, obviously the acceleration of the elevator with respect to the elevator will be zero, no? I mean, it's like this. If you are in the elevator's frame, what does the elevator look like to you? It looks stationary, no? So you can understand that mathematically also, but it's I mean, it's a logical conclusion, no? That any body A in its own frame will have how much acceleration? It will be zero, because it is basically acceleration of A minus acceleration of A. So like that, the elevator's acceleration in its own frame is zero. Understanding, no? So if you're standing inside the elevator and you see any part of the elevator, like, you see this wall of the elevator, or you see one of the lights which are attached to the ceiling or something, nothing of that is moving with respect to you. ना वो फ्रेम में उसका डिस्प्लेसमेंट ही जीरो है, so obviously उसका एक्सेलरेशन और वेलोसिटी भी जीरो होगा. Okay, now let's come back to the third part of the question. We wanted to calculate the reaction force at the hinge, the pulley. So reaction force, let's say R, acting on the pulley. Okay, through its hinge. So for this, all we need to do is we need to make. So you want to finish writing down that part? Okay. Okay, so done with this. Let's move on to the last part. Yeah, so next, what you have to do is you have to just make the free body diagram of the wedge. And since, sorry, not the wedge, the pulley. Okay. So the disk of the pulley is massless, so it doesn't really matter what reference frame we do it in, because neither it has weight nor pseudo force now. The mass of the pulley is tending to 0. Okay, so its weight is tending to 0. Pseudo force on it is tending to 0. So it doesn't really matter which reference frame we make it in, whichever non-reference frame, non-inertial frame or inertial frame, there will be only the external forces acting on it. So those are, the thread is, from both sides is applying downward tension. Okay. And this is trying to pull the pulley down, but through the axle of the pulley, there is the vertical external force, the reaction force R. So R has to balance 2T. This, okay. This is like the third equation. Now go back to equation 1 and 2. We had T minus this, okay. And we had so this equation had become T minus 4 into 12 was 4A, and this equation had become 6 into 12 minus T is equal to 6A. Now we'll solve this for T now. Okay. So from equation 1 and 2, A is becoming T minus 48 by 4. And from equation 2, that is the same thing as 72 minus T by 6. Okay, so we can solve for T. Sorry, my mistake. This should be plus. This is the tension. So now just plug this in into that equation. So reaction force will become 2T. Or you can just substitute the value of A in this also. A had come out to be 2.4 meters per second square. So you can see T is equal to 48 plus you can do that also. So anyhow, this part is just algebra. The important thing is to understand the free body diagram and its application. Okay, people. So I hope this is 100% clear to all of you. So you will find plenty of questions like this in HC Verma exercise of Newton's laws of motion, as well as in your module. Okay. So whenever you have a situation where you're trying to solve the equation of motion or the acceleration, etc., of a body which is in a frame which is already moving with acceleration, you have to remember to apply the concept of non-inertial frame and include the pseudo force in your free body diagrams, like we have done in the first part of the question for these two free body diagrams. Okay. So we are looking at the motion of the two blocks inside an elevator which is accelerated. So we have to solve their free body diagrams with respect to the frame of that elevator, na? Because the pulley is attached to the elevator. In ground frame, it will become very complicated because the pulley itself is going up. So the simple way to solve the question we saw in the beginning itself is that we concentrate in that frame where the pulley is fixed. So the blocks are having a simple motion, that one is coming down, the other is going up with respect to a stationary pulley. So that is in which frame? That is in the non-inertial frame of the elevator. So that is why we have chosen that reference frame to solve the problem. That's why we have made the choice of this frame in part 1. And just because it's a non-inertial frame, so we have to be sure that we include the pseudo force to get the correct result. Okay, so now gradually we'll increase the type of variety of questions, including this pseudo force concept. So next we will see a more interesting problem where, let us now say we have a horizontally accelerated frame. Okay, like imagine a vehicle or something. Yeah, very good, Harsh. Thanks. So we have, let us say, this is the inside of a vehicle which is accelerated horizontally. So this is moving horizontally at something, let's say 4 meters per second square or something like that. Okay. And inside this, there is a inclined plane. So we have a smooth inclined plane inside this at an angle of 37 degrees. Okay. There's a smooth inclined plane. And a block of certain mass is released from rest on the inclined plane. So it starts sliding downwards like this. So we have to find out the acceleration of its motion. Okay. So a block of mass m equal to, let us say, 5 kilograms is released from rest on an inclined plane inside a moving frame, inside an accelerated box or something like this. Okay. So first of all, make the free body diagram of the block in the reference frame of the reference frame fixed to the inclined plane. Okay. And show all the forces. So obviously when we say make the non-inertial, make the free body diagram, we mean that we have to show all the forces. And then we want to calculate the block's acceleration with respect to the inclined plane. And we'll take the value of g as 10 meters per second square as usual. And once you've done that, we also want to calculate the normal reaction on it. Normal reaction force n acting on the block. Okay, so start with the free body diagram. If you just remember the concept of pseudo force in a non-inertial frame, it should not be too difficult. Okay. In the reference frame of this thing, no? the first part, see, it is saying in the reference frame fixed to the inclined plane. So the inclined plane is in which frame? It's in the frame of the vehicle only now. So that's what we mean by it now. So basically what we want is that we are in this frame. No? So with respect to this reference frame, we have to find the acceleration. E is the acceleration of the block with respect to the frame of the moving vehicle. Okay, that is the frame in which the inclined plane is fixed. That's one and the same as this. Right, Harsh? So hope this point is clear. So now you see when we are in that frame, we are talking about being in a reference frame where we are accelerated horizontally. You know? So our reference frame, which is the frame of the car or vehicle or whatever, that is having a horizontal acceleration a naught like this of 4 meters per second. So in that frame now, when we talk about this body on the inclined plane, what all forces will be acting on that? Let's see. Okay. So first and foremost, we have to understand that there will be pseudo force. And the pseudo force's direction will be like this. It will be opposite to the acceleration, and its magnitude will be m into a naught. So this will be our pseudo force. Whereas gravitational force will be vertically downwards, and normal reaction will be perpendicular to the inclined plane. Along this. So you can see that this angle is our theta equal to 37. So here this will also be theta. This will also be theta. And with respect to this system of axis now, and in this frame, this block will be having an acceleration down the inclined plane. So this is relative to the frame of the car. Okay, so this acceleration is the acceleration of the block relative to the non-inertial. Okay. So next step, what we do is we resolve the forces as usual. So we make a more convenient kind of free body diagram where weight के जो components हैं, you can show them first. The components of weight are mg sine theta and mg cos theta like this. Okay. So the components of weight are covered. Okay. Then let's come to the components of pseudo force. So this pseudo force will have a component down the inclined plane, a component normal to the inclined plane. So these are covered now. Okay. And then of course there's a normal reaction. So these are my forces. Right. And under the action of these forces, along my x-axis, there is an acceleration of E. Along the y-axis, there's no acceleration. So now you can just apply Newton's laws of motion for the two axes. Okay. and just get the values of E and N. That's all we have to do. Okay. Now, as far as the values are concerned, remember that E naught is given to us as 4 meters per second square. G is equal to 10. Theta is equal to 37 degrees. And mass of the block was 5 kg. So just use these values and find the equations to calculate N and E. Okay, so try to do this fast yourself. Okay, I'll put up the answers in a minute. All right, so let me put up the answers and verify it. Okay. So along the inclined plane, you can see your equation will be mg sine theta plus ma naught cos theta is equal to ma. And perpendicular to the inclined plane, you will see that normal reaction balances, or rather normal reaction plus pseudo force is sine component. This balance is mg cos theta. Okay. So let's see. So from equation 1, you'll get E is equal to g sine theta plus E naught cos theta. So substitute the values. So 10 into 3 by 5 sine 37 plus 4 into 4 by 5 cos 37. Okay, so that is 6 plus 16 by 5. So that is 3.2. Okay, so that is my acceleration. And from equation 2, we'll have n is equal to mg cos theta minus ma naught sine theta. So the mass was 5 kg. So this should be a normal reaction. Okay, so hope this question is fully clear. So these are some of the key type of applications of the concept of pseudo force. Now, next we'll see another interesting question related to this type of concept. And gradually we'll build up our variety of questions and you'll develop the experience required to be able to solve these type of questions. So from here on, it is just a matter of practice. Okay? You know more or less all the concepts required to solve these type of problems, whether it is to do with system of pulleys and constraint relation, or it is to do with solving Newton's laws in non-inertial frame and the concept of pseudo force. You have all the tools required to solve the questions, but it's going to take practice. It's going to take a lot of patience and a lot of effort on your part. But the idea is that you should, take it as a challenge, as a sort of fun activity, as an interesting challenge for you, something exciting to solve maximum problems and be able to analyze correctly uh, all problems in Newton's laws of motion based on free body diagram concept. So let's look at another practice example. So now this is again something that we should be able to relate to once we think about this carefully. This example I'm putting up. So imagine we have this triangular wedge, like a triangular block, like a even think of it like a glass prism, which you have placed on a smooth surface. So you have a polished smooth surface on which we place this triangular wedge of mass m and angle theta. Now this surface is also smooth. This is also a smooth surface. Okay. And what we do is we now place another smaller block on this. And the moment we place this block, we now start pushing this system with some horizontal external force F naught. Okay. In fact, we can just place this. Place it. Somewhere here also. Okay. So a block of mass, let's say 2 kilograms, is placed on the smooth inclined surface of the wedge of mass, let's say 8 kilograms, and angle of inclination, let's say, it's time for variety, let's say 30 degrees. Okay. When simultaneously the wedge is pushed with a Yeah, thanks for passing the host back to me. Yeah, let's continue back with what we are discussing. Okay, so let's come back to this question. So what's happening in this situation here is that yeah. So what's happening in this situation here is that we have this triangular wedge which is placed on this smooth horizontal surface, and we place this block gently on it, and simultaneously the wedge is pushed with a constant horizontal force F, such that the block will remain stationary with respect to the wedge. Okay. Now this is where you have to actually visualize this. Take a moment, that even though this is a smooth plane, but if we push it with enough force, there will be enough acceleration in the system that this block will not be sliding on the wedge. In the wedge's frame, it will remain stationary on the inclined plane. So it will remain stationary with respect to the inclined surface. Okay. So we are doing this. We are applying the force in such a way that this is happening. It remains stationary with respect to the inclined surface. So for that to happen, we have to find out how much force we have to apply. So first part, what we'll do is we'll find out the acceleration of the wedge with respect to ground, of course. Okay. And we will find out the magnitude of force we are applying. So we'll find out this acceleration in meters per second square, the numerical value of the acceleration in meters per second square. And we will find out the force in newtons, taking the value of g as 10 meters per second square. Small m, capital M, and theta are all given to us in the question. Small m is 2 kilograms, capital M, the wedge's mass is 8 kilograms, and theta is 30 degrees. Okay. So start working on this question. Now, the hint to you again is that to find this out, now what you do is you make the FBD of the wedge, of the block in the non-inertial frame of the wedge. Okay. And remember, in that frame, what should happen? The block should be stationary. It should remain in equilibrium. So from that, you will get the required condition. Just try this out. You will get it from that. Okay, so let's try to understand how this is possible, that in spite of the surface being smooth, but intuitively we are understanding कि अगर इसका acceleration fast enough है, this block will have a tendency to remain pinned on that surface and will not slide. So how that is happening in terms of forces, how we can explain that phenomena on the basis of Newton's laws of motion. Let's try to understand that first. Okay, so what we are suggesting here is कि यहाँ पे this force that we are applying is giving this system enough acceleration so that the block kind of remains stationary on the wedge as it moves. So we can think that the block plus the wedge as a system, it moves with a common acceleration A like this, but the wedge remains at rest with respect to the block remains at rest with respect to the wedge. Okay. So what we will see is that one moment the system is here when we start applying this force, and with this force continuously acting, after a while this system would have displaced like this. The whole thing is displaced together from here to here. Okay. So now let's try to understand how this is happening exactly. So for that, let us imagine that we are in the frame of the wedge. Okay. So let's imagine that what's happening is that we are standing on the wedge. Our reference frame is attached to the wedge. So what we see that in our frame, this is at rest. Okay. But then remember, we are what type of frame? We are a non-inertial frame because the wedge itself is traveling with an acceleration in the ground frame. Okay, so let's keep that in mind. So we are in that non-inertial frame. Okay. Now I don't know right now how much the acceleration is, but I know the direction of the acceleration. This non-inertial frame is having an acceleration, horizontal acceleration towards the left of some value E. Okay, so I don't know as of now how much that acceleration is. I have to calculate that for the condition for this block to remain at rest. So in this frame now, let's figure out what all forces are acting on the wedge, on the block. Which should be at rest in this frame. It is at rest in the non-inertial frame. Okay. So the forces acting on it, first and foremost, there is the pseudo force we have to account for. So the acceleration of this non-inertial frame is towards the left. So pseudo force uske opposite hoga. Pseudo force will be a force like this. This is my pseudo force. Okay. And the rest are, as you know, the regular real forces of weight which the earth is applying downwards on the body, and the normal reaction. So the normal reaction that this surface is applying, because it's a smooth surface after all, so there's no friction. Friction we will come to in the next chapter after we complete this Newton's laws part. But now this one's acceleration should be zero. They should be at rest. So these forces should balance. So just apply the condition for the forces to balance. You can either resolve the forces, or you can use Lami's theorem method also. So for example, here you can see this angle will be 90 plus theta. Okay. Whereas this angle will be 180 minus theta. Whereas this angle will be 90. So the condition for the vector sum of the three forces to be zero, you want net force to be 0. So this is the resultant of these three forces. Okay, that will give you that mg divided by sine of this angle is equal to pseudo force divided by sine of this angle is equal to normal reaction divided by sine 90. So mg upon cos theta is equal to ma upon sine theta is equal to n. So you can see that we will get A is equal to g tan theta. So that is the result that we were looking for in the first place. So theta is, remember, 30 degrees. So it will become 10 by root 3 meters per second square, and n will become mg by cos theta. So that will become 2 mg by root 3. This will be the normal reaction. But anyhow, here we are more interested in the value of acceleration. That was the first part. We wanted to calculate the acceleration of the wedge so that the block remains at rest on it. So hope this is clear, people. Just make a note of this. This one, this theorem, Bhargav, okay. This is, no, this theorem that if we have three vectors, and we want to solve for the condition for A plus B plus C to be 0, then suppose opposite to A, this angle is alpha, opposite to B, this angle is beta, and opposite to C, this angle is gamma. We get the result that A by sine alpha is equal to B upon sine beta is equal to C upon sine gamma. Okay. Now, alternately, we can also resolve. We need not use this. Another thing we can do here, we can also do by resolution. By resolving, we can look here that, so for example, mg के जो components है, they will be mg cos theta, mg sin theta. Okay. Then pseudo forces components will be ma sin theta and ma cos theta. And then there's normal reaction. So there is this. So since we have to balance the forces, you can see that along this axis, along my inclined axis, mg sin theta has to balance ma cos theta. Okay. So this will actually give me the same result, that E is equal to g tan theta. Okay. This will give me this result. Same thing as I've got here. And then you substitute this in the second equation, that normal reaction is equal to mg cos theta plus ma, sorry, this one will be sine component. Just make a small correction here. This is the cos component and this is the sine component. Okay. So from this you can see that n will become when you substitute this now, you get this like this. Now see A's value is this. Okay, so this will become mg upon cos theta. It will become like this. So when you solve this further, so that will be this. So it can also be shown from free body diagram. Yes, this is the sine rule of triangles. Trigonometry mein you would have studied this, no? This is the sine rule of a triangle. Because if the sum of three vectors is, you haven't said, so it doesn't matter. You can do by the resolving method also. Okay. Otherwise, you can look this up in your module also. This is called Lami's theorem. Which is the same thing as sine rule in trigonometry. You can just remember the statement of this and see how you applied this here. So anyhow, just make sure you understand up to this thing first, how we got the value of acceleration. Okay, then we'll come to the second part, the same as this. It's just an alternate way of solving the equilibrium condition, which you can always solve by resolving otherwise. Okay, people. So next up, let's look at how we calculate the force. Yes. So Harsh, that is correct. So once we have understood that the relative acceleration of the block with respect to the wedge is 0, that means in the ground frame they have the same acceleration. Okay, so that's the next thing. Okay. So what we have understood is that the acceleration of the block relative to the wedge or with respect to the wedge, that is 0. Okay. So that means acceleration of the block with respect to the wedge is 0. So that means that in ground frame, acceleration of the block is equal to acceleration of the wedge. They're both moving with the common acceleration. This whole thing is moving with the common acceleration E, like this. Okay. So now what we can do is, so since they are moving together, we can make a combined FBD, make a combined free body diagram for the block plus wedge as a single body. Okay. So think of that whole thing like one single mass M plus capital M. And on that mass, what all forces are acting? Horizontally, there's only one force. Rest is vertical. There's some normal reaction from the ground. Okay, and this is of course an inertial ground frame now. This is with respect to ground. So in this frame, this is having an acceleration A like this. So F should be equal to M plus ME. So this becomes our equation. Now from the earlier free body diagram, from part 1, we saw that this acceleration was g tan theta or 10 by root 3 meters per second square. Therefore, F just becomes whatever the sum of masses was, 2 and 8 kg. Okay, so F is equal to 100 by root 3 newtons. Okay, this is the easy way of solving this. Okay, so this is the preferred method. Now, on the other hand, we can also make the free body diagram of the wedge alone in the ground frame. Okay, in inertial ground frame. But the problem with that is then we'll have to see that, okay, F is acting like this, but there's also normal reaction that the block is applying on the wedge. So we'll get the same result from this, but we'll have to then, resolve this normal reaction and all. So you'll see that this normal reaction that is acting, this angle was theta. So this angle will be theta. So if I go with this, I'll have to, do all this, that F minus N sine theta is equal to capital MA. Okay. And then from the earlier equation, we have to substitute N's value as small mg by cos theta and substitute the value of A as g tan theta. Now doing that, we will get the same value of F. We'll get this same answer. So when we substitute these two here, this will give us the same result. Yes. Okay, so make a note of this, please, people. And with this, we conclude today's session. So now you're really going to be in a position to wind up Newton's laws of motion in terms of questions. And next session will purely keep for discussion of questions and doubts from H.C. Verma as well as from the module. So prepare accordingly, okay, so that we can wind up Newton's laws of motion chapter and then move on to friction after that. Okay, so please work accordingly, and we'll discuss questions in the next lecture. That's it for today, people. Wish you all the best.